Today's video will define the levels of the software design metric of robustness. Hello, I'm James Helfrich. Customers want reliable code. They want code without bugs. But how do you know how much confidence you have in a given piece of software? Well, the software design metric of robustness is designed to measure that, and there are 5 levels. So what is the software quality metric of robustness? Now, robustness is the degree in which a function, a class, or a component has been tested to ensure it functions as designed. Robustness is important because it gives the client assurances that the code they are using can be trusted to work as expected. The higher the degree of robustness, the more it can be trusted. Now, in this case, I want you to think of the client and the provider. The provider is the one who wrote the function, the class, or the component, and the client is the one using it. The client is also a software developer. Now, when you hook up someone else's code, how sure are you it's going to work the way you want it to? Well, robustness is the degree of assurance you have with that. And we have several levels of robustness. The highest is proven, which means the design has been formally proven to be robust. And this does happen in high stakes scenarios, but is not the most common scenario. Resilient, thorough white box testing. Usually we use unit testing to achieve resilient level of robustness. Strong, rigorous, and systematic black box testing. Then we have tested, some ad hoc black testing, and then fragile, which means we have not done sufficient testing. It may still work, but we just don't know for sure. Let's look at each of these in turn. First of all, the lowest degree of robustness is fragile, where the class can only be expected to work in very restricted circumstances. Fragile is the default degree of robustness, the degree in which we can assume all software has been first written. In other words, we haven't done any testing yet. This is often the case early in the software development cycle. So, question, why does code remain fragile? Well, first and foremost, the developer thinks it's too simple to be worthwhile to test it better. In other words, we look at it and we say, that probably works. And let's be honest, we've written a lot of code for this exact reason, haven't we? Number 2, it seems like it works. I've run through a few rudimentary tests and I'm confident enough. In other words, my nervousness about the complexity of the code does not sufficient to warrant making more rigorous tests. And finally, there's not sufficient time to create or run more thorough tests. It does take time and effort to test your code, and we're thinking we're going to save time by not testing it. And this might be true for very limited scenarios, but for the most part, fixing bugs is really expensive. The longer it's been since you found the bug till you fix it, makes a bug more difficult to fix. So by not thoroughly testing our code initially actually decreases our efficiency of writing code, does not actually save us time. So that last one is actually a lie, but the other two are the most common one we see. Okay, so we're going to go one level better than fragile. We're going to go to tested. A class or a function or a module can be considered tested when it has all the mainstream interfaces have been tested and all the core scenarios have been validated. And the tested level of verification could be termed ad hoc, in other words, non-systematic, black box, I'm not looking at the internals, testing. So for an example, I'm going to create a little bit of code here at the beginning of main that's going to let me run through a whole bunch of test cases to my function or class in quick succession. I'm not doing it in a systematic way, but I am actually testing the code a bit. This is going to be a much higher level of assurance than I had before with Fragile, but it still leaves a bit to be desired. The next highest level is strong. A class exhibits strong robustness when it has been rigorously verified. This occurs when a thorough test plan has been developed and been systematically executed. In most cases, this involves a test plan and a test harness. So what we're going to have to do is for every function or class, we're going to take a look at this and we're going to come up with a set of test cases. And we're going to say, for an example, if I'm playing Sudoku, I want to know if a given number can go in a given position. So I'm going to try, hey, what if there's already a number on that row or that column or that inside square, or there's no number there, or my coordinates are invalid, or my number is invalid. I'm going to generate all these test cases before, and then I'm going to run through them. Now, notice this is black box testing. In other words, I'm not looking inside the code. I'm not checking these with asserts. I'm just doing my user input. And so this gives me much more confidence that my code works than it did before when it's fragile or even tested, but there's still an opportunity for there to be bugs. Okay, so what could be better than strong robustness? The next level is resilient. Resiliency is a high degree of robustness characterized by exhaustive unit tests. So on the left here, I have a single test case where I want to test a velocity class. So I'm going to set the preconditions. I'm going to set my dx and dy to 2.3 and 4.5, and then I'm going to add 4.1 to my dx, and then I'm going to check to make sure my member variables are set as correct. Now notice I'll have access to the private memory variables of my class. That's why it's white box testing. And the accumulation of all these tests, which is on the right there, is going to give me that assurance that there are no bugs. And that's what we really want. We want to be at least resilient with most of the code we write. Now, the question is a complete set of test cases robustly tested with unit tests? Could there be anything better? And the answer is yes. Proven robustness is when a class has been mathematically proven to be correct for all input. So for an example, here I have a Swift binary search algorithm. Now, in order to make this proven robustness, I have to reduce this to a math equation, and then I have to mathematically prove that for all input, we have the output we expect. Now, as you can imagine, this is much harder than writing unit tests, and it's much, much harder than just running through a bunch of ad hoc tests. So why in the world would I ever want to go through all this work? Now, libraries often need to be proven. If I'm going to work on the standard template library or the .NET framework or something like that, I really need to make sure that all the bugs have been found, so it's worth going through the extra work. Now, difficult code to debug often benefits from proven reliability. And the poster child for this is if I want to thunk. If I want to go from a 16-bit to a 32-bit system, it's very, very difficult to debug across those lines. I mean, extremely difficult. So it's actually time effective for me to have proven robustness, to mathematically show that everything works, rather than try to go through the very painful operation of doing the debugging. Finally, mission-critical systems such as aerospace, security, and medical applications, there can have legal or contractual obligations. And in that case, it makes sense to be proven. So if I'm going to write any code that like an embedded system where it's really difficult to update it, or if it's going to be involved in a self-driving car, or if I'm going to be a defense contractor, or if I'm going to work on some medical equipment, I mean, all these things, we really, really, really need to make sure that it works. And it's going to take a lot of work to do this mathematical proofs. But the benefits are there because we have contractual obligations to do so. Now, we can learn more about this in the fragile robustness, tested, strong, resilient, and proven sections of the robustness chapter of the software design textbook.